When we first model light, we often rely on geometric rays, mathematically treating light as an infinitely thin, one-dimensional line. In standard wave theory, we use plane waves, which assume an infinite, uniform width across the entire direction of travel. Neither of these models describes a real laser. On the right, a geometric ray has no width. On the left, a plane wave has no edges. A real beam exists between these extremes, possessing a finite waist that eventually expands into a cone. This expansion is driven by diffraction. When an electromagnetic wave is confined laterally, the physics of waves forces it to spread transversely as it propagates. To model a beam with a finite width, we have to move past simple geometry and derive a specific solution directly from Maxwell's equations. Our derivation will rely on two constraints: the monochromatic approximation, assuming a single color, and the paraxial approximation, assuming the beam travels at small angles relative to its axis. The resulting Gaussian profile describes how the electric and magnetic fields arrange themselves to stay confined while satisfying the laws of wave propagation. The derivation begins with Maxwell's equations in a source-free vacuum, where charge density and current are exactly zero. By manipulating these equations, we can isolate two primary terms: the spatial curvature of the field and its temporal acceleration. Linking spatial curvature to temporal acceleration forms the standard electromagnetic wave equation. Next, we apply the monochromatic assumption, focusing on the single pure frequency from a high-quality laser. This lets us express the electric field as a spatial pattern oscillating uniformly over time. When we substitute this oscillation into the wave equation, the time derivatives resolve cleanly, allowing the time-dependent components to cancel out of the expression. This leaves us with the time-independent Helmholtz equation, which describes the spatial geometry of the field. Here, the wave number k represents the spatial rate of phase change, tracking how many radians the wave ripples per meter. While the Helmholtz equation is valid for a single wavelength, it still allows for waves traveling in any direction. To find a narrow beam, we need to apply a geometric restriction. We apply the paraxial assumption, which assumes the beam's energy is concentrated in a narrow cone around a single axis of travel. Because the beam is narrow, the angles of propagation relative to the axis are much smaller than 1 radian. This allows us to factor the field into two multiplicative parts: a fast carrier wave and a slow envelope. The carrier wave handles the rapid, microscopic phase oscillations occurring every wavelength. The envelope U describes the macroscopic width of the beam and its gradual expansion. Applying the product rule to differentiate this field results in this expanded expression. Because U changes slowly compared to the wavelength, its second-order longitudinal derivative is negligible and removed. This simplification results in the paraxial wave equation. Dropping that single second-order term changes the nature of the math, shifting it to an equation that exclusively governs the evolution of the beam's envelope. The TEM00 Gaussian beam is the fundamental solution to this equation. The master formula separates into two parts: real amplitude terms and complex phase terms. The amplitude term reveals a smooth transverse bell curve that peaks on the central axis and fades toward the edges. The beam radius W is the distance where field amplitude drops to 1/e of its peak. Because optical detectors measure intensity, the square of the field, we square the exponent. At radius W, intensity drops to 13.5%. The beam waist is the absolute minimum radius, occurring at the focal plane. The Rayleigh range is the distance along the axis where diffraction causes the beam radius to grow by a factor of the square root of 2. At this distance, the beam's power is spread over twice the area, which drops the peak on-axis intensity to exactly half. Far from the waist, the beam spreads at a constant divergence angle. Inversely, a smaller waist size leads to a much larger angular spread. The product of waist and divergence angle is constant. This is the Gaussian divergence limit. A beam focused tighter will always diverge more rapidly. Now we examine the complex phase terms. These dictate exactly when the electromagnetic field reaches its peak at any given point in space. The first term, kz, represents ordinary propagation, the same phase advancement you would see in a simple plane wave. The radial phase term is controlled by the radius of curvature. At the waist, this radius is infinite, creating perfectly flat wavefronts. As we move into the far field, the radius of curvature matches the distance from the focus, generating spherical curves. In this far-field region, the beam behaves like a spherical wave spreading from a point source located at the waist. The final term is the Gouy phase shift, governed by an inverse tangent function. As the beam travels through the focal region, this phase rises smoothly from negative pi/2 to positive pi/2. Physically, this shift occurs because a confined beam is composed of waves traveling at slight angles. These off-axis components travel slightly slower along the axis, resulting in a total phase lag of pi as the beam passes through the focus. These phase terms provide a precise map of the physical curvature and timing delays inherent in any focused wave. The TEM00 equation we derived provides a description for a theoretically ideal beam. However, actual laser cavities are rarely perfect. Real-world factors like mirror misalignments, thermal lensing, and optical aberrations degrade the beam's quality. These factors allow higher-order transverse modes to survive. Unlike the single Gaussian lobe of the fundamental mode, these higher-order modes have zero crossings that create multi-lobed intensity patterns. To measure how close a real beam comes to the ideal Gaussian, we use the beam quality factor, or m². An ideal diffraction-limited beam has an m² of 1. For any real beam, m² is greater than 1. This value acts as a multiplier on the divergence angle. If a beam has an m² of 1.5, it spreads 50% faster than an ideal Gaussian with the same waist size. This excess divergence also compresses the Rayleigh range, shortening the distance over which the beam stays tightly focused. In practical terms, a beam with a higher m² requires a more careful trade-off between the focus size and the available working distance. m² serves as the final link between electromagnetic theory and real-world engineering, providing the metric required to predict exactly how a real beam will behave.